Oh, howdy there! Aren't you just a bright ray of sunshine on a cloudy day? Come on in, let's talk about some mathematics. Today we're doing 5.2, verifying trigonometric identities. Alright, so hopefully at this point from the last section, we're okay, we're getting a little bit better at actually using some of these trig identities. And when we get into this 5.2 and verifying, it won't actually be too bad, because verifying trig identities is very much like what we were doing before and kind of manipulating the expressions. We're kind of just putting it to use in this next one. Alrighty, so here's what we are going to do. I'm going to skip through all of this stuff because it's not important. We just have some guidelines for how we're going to go about doing this. Each side of the equation obviously is an expression, so we're going to be using the tools that we did in the last section to work with one side of the equation at a time. Don't bite off more than you can chew, trying to mix and match both sides to make them look the same. We want to look for opportunities to factor an expression, add fractions, square binomials, create monomial denominators. We want to look for opportunities to use the fundamental identities. That is key. Okay, constantly looking for ideas and opportunities. When the preceding guidelines do not help, try converting all terms to sines and cosines. We'll look at an example where we do that. And then always try something. Okay? There is always something to do. There are so many different methods to doing these. And even if you go and you go and you go and you go and you realize that you're not getting anywhere, it still gives you some sort of information toward the next time when you go to do it. You'll think, okay, well, this type of idea is just going to bring me in circles. I know that, so why don't I try something different? Okay, always try something. What we want to do with this first one is verify. Now, by verify, I mean that I want both sides of the equation to look identical. Okay, and like one of those bullet points before was saying, I could mix and match and mess with this side and mess with this side, but stick with one, simplify it, verify that they can equal the exact same thing. Now when I look at this, my first thought is, okay, this left side is far too complicated, and I can already see that there's some things in here that I can mess with and make it look like the sine squared. And the sine squared is pretty simplified. There's not much that I can really do to it unless I wanted to expand it and make it more complicated. So why not just make the complicated side simple? Alright, so what I am going to do here is just look at this. Secant squared of theta minus 1 over secant squared of theta. So what can I do to try and mess with this thing? Now there are different methods as to how I can go about it, but I think what I'm going to do is kind of like what we did in the last video. I'm going to go ahead and split the fraction. I'm going to have secant squared over secant squared minus 1 over secant squared. Alright, so what has that done for me? Secant squared over secant squared is 1, and then minus 1 over secant squared. That is cosine squared, because secant and cosine are related by reciprocal identity. So now that I have 1 minus cosine squared, this should hopefully start to ring a bell in those brains of yours that it's something to do with the Pythagorean identity. And it is. If I rewrote sine squared plus cosine squared equals 1, in a way where sine squared was by itself, I would be subtracting cosine squared. So sine squared equals 1 minus cosine squared. So I have effectively simplified the left side of the equation down to sine squared. So now I can simply say sine squared equals sine squared, verified. I always drop off the thetas because I get so excited and I stop putting the variables in there. It's very bad of me. Alrighty, so I took the complicated side, I simplified it down, made it equal the same thing as the right side, and I was good to go. Let's look at a different one that's more to do with fractions, and I know when I'm faced with something like this, what I'm going to look to do is combine the fractions. Okay, the left side of the equation, again, obviously, it looks a lot more simplified than the right side. The right side, I can't do much with it because I have two different fractions and they're not the same thing and they don't have common denominators, and it's making me want to cry, and I don't appreciate it when they like this because it... Okay, all right, okay, I'm fine. So let's just go. All right, I'm gonna work with the right side, and I'm gonna make it work. I'm gonna make it work. What we would do to make these things work and to be able to combine these is I would need a common denominator, which is going to be 1 minus sine of alpha times 1 plus sine of alpha. And we know this why. If I can't clearly see that there are two things, a common denominator between what you're going to do is multiply those two together sine of alpha in order to create what you know is 1. So once you multiply those two things together, you get that common denominator. But in order for that to have happened, I would have had to multiply the left side by 1 plus sine of alpha over 1 plus sine of alpha. And I would have had to multiply the right side by 1 minus sine of alpha over 1 minus sine of alpha. So our tops here, this one gets multiplied by that, this one gets multiplied by that. So on the top, I actually have 1 plus sine of alpha, and then plus 1 minus sine of alpha. So it doesn't really look like I did much to help in the way of making it less complicated, but if you stick with me, I promise it'll be okay. I have a positive sign, and I have a negative sign, and then I have 1 plus 1. So the top becomes a 2. The bottom, when I multiply, 1 times 1 is 1. Negative sign times 1, positive sign times 1, those things are going to cancel. I'm going to have a negative sine alpha and a positive sine alpha. The middle terms cancel. Now my last term, negative sine alpha and positive sine alpha, becomes negative sine squared of alpha. So, now who made things simpler? This guy. Woo woo! Now again, this should start setting off alarms. 1 minus sine squared of alpha, that's got to be a Pythagorean identity. 2 over cosine squared of alpha. In fact, it is. I have changed the denominator from here to here. Now all I have to do is rewrite. What is that thing that's a reciprocal to cosine? Oh right, it's secant. So if I don't want cosine in the denominator, I'm going to change it to secant squareds, and the 2 will just multiply it. Because this is the same thing as 2 times 1 over cosine squared of alpha, which changes to that. Beautiful. So the important thing here to recognize is that I needed to combine these fractions before I could really do anything substantial. And in order to combine those fractions, I needed a common denominator, which is found by multiplying each individual fraction by the denominator of the other. The next one that we have here, I could really choose either side to work with. I guess I'll use this one. Both sides are equally simplified. I think I want to use tangent and cotangent just because they're a little bit easier to work with as opposed to secant and cosecant, because these are 1 over sine and 1 over cosine. These are more straightforward. So let's just do this side. Tangent of x, and this is plus cotangent of x. Alrighty. Now, how can I possibly combine these two things? Technically they'd be over 1. They're two completely different functions. I can't really add them or anything. But there is a way that I can look at them through a different lens and possibly be able to add them. Tangent we know is sine over cosine. And cotangent we know is cosine over sine. Which means in this case that I might actually be able to do some combining after all if I make a common denominator. So I'm going to multiply this side by sine over sine, multiply this side by cosine over cosine, and it's basically like what I was doing in the last example, where now I get the common denominator of sine cosine, and on the top I'm going to get sine squared plus cosine squared. Awesome. So now on the top Please, please, please tell me that you are starting to recognize the Pythagorean identity. Sine squared plus cosine squared is 1 over, and then I still have sine cosine. And now that we have this set up in this way, I have 1 over sine times 1 over cosine. Oh, please tell me that you are seeing this connection here. 1 over sine and 1 over cosine. That's going to be secant of x times cosecant of x. Beautiful. We have proved the left side is equal to the right side, and we're done. Fantastic. I think we have maybe one more to go. In this example, hopefully we're able to recognize now that you would probably start by working on the right side, because the left side is a little bit more put together. So on the right side, let's just pull that one over here and see if we can work with it. Cosine of x over 1 minus sine of x. I'm looking at this idea here where I need to simplify, but I have this messy thing on the bottom here which isn't really helping me at all. And you might be thinking, that reminds me of the ones we did last time where we had to multiply by the conjugate, which would be a fantastic idea. All of those who are thinking it, which I'm sure there were all of you. Boom, boom. Multiply by the conjugate, essentially multiplying by 1, so I'm not changing the fraction. On the top, I'm going to end up with cosine plus cosine sine. And on the bottom, I keep dropping the variables. Bad, bad, bad. On the bottom, I'm going to get 1 minus sine squared of x. Beautiful. Now I have some things that I can mess with, because I know that 1 minus sine squared of x, because I'm so good at using Pythagorean identities, is actually cosine squared. And on the top, should we do anything with it yet? Nah, let's leave it. Cosine of x plus cosine x sine x. Cool. Now I can split it. I can use this part, circle that, and alternately I can use this part, and I can just simply add the two together. So what I'm going to get is cosine of x over cosine squared of x, which you might realize is going to simplify a little bit, and cosine x sine x over cosine squared of x. So I get some really cool stuff that's going to go on here. I have cosine over cosine squared. That's basically like 1 of something over itself times itself. Like, for example, x over x squared. That equals 1 over x. Because I have 1 on the top and I have 2 of them on the bottom. So this is going to end up being 1 over cosine of x. And over here, this is going to be, I have a cosine on the top and I have 2 of them on the bottom. So boom, boom. 1 times the sine of x over cosine of x. So tell me, what is 1 over cosine x? I'm going to hear you all shouting from your homes, secant of x! And what is sine over cosine? It's tangent! Beautiful. I'm so happy for all of you, and I think that's the end. It is the end. Woohoo! I wonder if we got it done in record time. Probably not, because I tend to be long-winded and throw too much into these. So, do these hand exercises. Good luck. See you in class. Fare thee well.
I didn't know any of this stuff. Like cosine? That's so interesting. I'm probably going to use that a lot in real life. Especially if I become an English teacher.